Hello, this is Dr. Lori. Welcome to this video demonstration of the Pearson correlation in SPSS. So for this particular analysis, we'll be using a data set called Class Survey. It's actually found in the appendix of your SPSS Using SPSS Statistics textbook. I've gone ahead and entered the data here so that you already have it and you don't need to do that data entry. However, if you're interested in doing the data entry, I'm sure it would be good practice. So I wanted you to know where that was. With the Pearson correlation, there are two assumptions that are really important that need to be met. First of all, the residuals need to be normally distributed. And remember, we're looking at the relationship between two continuous variables with Pearson correlation. And also, if we're looking at that correlation, that relationship then needs to also be linear. So it needs to be a straight line. If it's a curved line, then SPSS or this correlation tries to fit a straight line to it, and it won't fit the data points like they're designed to be. So it needs to be linear or a straight line, and it also needs to be normally distributed. So in terms of data entry, it's already done for you, but you can see that each row represents a case, and this is a survey of a class. You can read more about it in the appendix, and you can kind of see what the different variables represent. There's class 1 and 2, that stands for morning and afternoon. You can see we have different genders, their predicted grade in the class, how much anxiety they have around this particular class and how they rated their instructor, as well as the points they earned on exams 1 and 2. So there are a variety of different variables that are included in this data set. For this Pearson correlation, what we would like to do is 3 steps in our data analysis. First of all, we would like to look and see how we check for linearity, and then the second step will be how we check for normality, and then the third step we'll get around to actually calculating the correlation coefficient. So let's go ahead and go to our first step, and we're going to make a scatter plot and see how that data looks on a graph that plots the x variable along the x-axis and the y variable along the y-axis. So we go to Graphs, Chart Builder, Scatter Dot. I need to reset this. And then this top left one, I'm going to go ahead and drag that up to the chart preview area. And then I need to put exam 1 along the x-axis. We want to see if exam 1 will predict exam 2 on the y-axis. Then we're going to click on OK. So here's my graph. You can see there are some low points and some high points over here. So we have a wide variety. One of the things that I can do here is I can actually open this graph and I can add lines to it. Like here's kind of a best fit line. Let me move this over to you so you can see what I'm doing. And then once I added it, I closed it. And you can see it gives us an equation there. So I can have that line be there. Once I'm done with it, I close it, and any changes I made are left then on the graph. But you can see, there's kind of like a relationship. That's the line that's collectively closest to all of those data points. So it looks like there's kind of somewhat of a relationship there. So the second thing that we want to do is we want to check both variables for normality. And so here's one time that we're going to use the nonparametric tests as they're set up to be. So we're going to go to Analyze, Nonparametric Tests, and we're going to ask for 1 sample tests. And it opens this dialog box right here. You can see at the top there are 3 tabs: Objectives, Fields, and Settings. If you're in a PC, your tabs may look a little bit different, but they're still the same tabs. Under the Objective tab, we want to click on Customize Analysis. When we click on the Fields tab, what you may notice if you do this is you may notice that all of these other variables are also included over here automatically, and you can click on them one at a time and move them over if you have too many variables over there, or you can click on one, hold down the Shift key, and then select all of them and move them all over at once. What you want to end up having is, for the test fields, only the 2 variables of interest. And so specifically we're evaluating the exam 1 and exam 2. So that's the only ones we want to have on that list. And then use custom field assignments. We want to click on Customize Tests and then Tests for the Kolmogorov-Smirnov test. So we want to select this one right here. And then we click on the options and make sure that the normal is checked and click OK. Once we have all of that set up, we've clicked on the Objective tab, the Fields tab, and the Settings tab. Then we're going to go ahead and click Run. And the interesting thing is it gives us the answer to our question. Our question was, are the points on exam normally distributed? And so right here it says the distribution of points on exam 1 is normally distributed, and it gives us a mean and the standard deviation, and our decision then is to retain the null. In other words, we fail to reject it. We don't reject it. The second part is we're testing whether the exam 2 is normally distributed. And again, this test tells us, yes, indeed, both of them have the same result. Both are normally distributed. So now we've checked for linearity with the Scatterplot. We've checked for normality with our nonparametric KS test, Kolmogorov-Smirnov test. So the one thing that's remaining is we want to actually calculate the correlation. So let's go to Analyze, Correlate, Bivariate. I'm going to reset it. And we want to put these 2 exams in here. We want to make sure that Pearson correlation is selected, and we leave it as a 2-tailed test. That's kind of the default. Check this box, flag significant correlations if it's not already, and then click OK. Now, the interesting thing about this output is that it doesn't look like there's much here, but it really does give us quite a bit of information. So first of all, we need to understand exactly what it's showing us. Here we have points on exam 1 and points on exam 2. So points on exam 1 is the top row, points on exam 2 is the bottom row. And we're showing correlations with points on exam 1 and points on exam 2. Now, you would assume that points on exam 1 would have a perfect correlation with itself, and it does. And so the Pearson correlation here is 1. The n is 32. They don't bother calculating a significance because that really is not very meaningful. And the same thing happens on this bottom row, points on exam 2 correlated with points on exam 2. So that doesn't give us a whole lot of information. It's the diagonal boxes that are going to give us some kind of information. So the correlation here, points on exam 1 with points on exam 2, is 0.536. And then we can convert that to a p-value, which is the sig here, the 2-tailed significance, which is 0.001. Now, if we remember about our standard cutoff of 0.05, this is statistically significant, this correlation between the two. And more than that, we can actually say whether this is a kind of a weak correlation or a moderate correlation or a strong correlation. So if we look at that Pearson correlation, which is also known as R, we can compare that to the information that you have in your handout. Different people will use different cutoffs, but in general, 0.1 to 0.3 is considered a weak correlation. 0.3 to 0.5 is kind of moderate, and greater than 0.5 is considered to be strong. So this is kind of like right on the verge between moderate and strong. And so you could probably call it either one. If it was really high, then you would probably call it strong, and if it was lower, those aren't hard and fast cutoffs, but it gives you kind of a general sense of where you are. Now, the fact that it's positive, it's a positive number, 0.536 is a positive, it doesn't have a negative dash in front of it, means that as exam 1 goes up, then the points on exam 2 also go up. And so we saw that when we looked at the scatter plot. As exam 1, the points increased, exam 2 also went up. And so people who did well on exam 1 also tended to do well on exam 2. A negative correlation would be a slope that's down and to the right, and so the line would go the other direction. And there's something that I want to point out pretty strongly, which is that Pearson correlation doesn't tell you the slope of the line, doesn't tell you how steep it is. Rather, it tells you how close these little dots are clustered to the line. This is a pretty good fit. You can see the cloud is kind of like elongated and football shaped. If this was just a totally round circle, then that would be a Pearson correlation of 0. And if all of the dots fell exactly on the line right here, then that would be a Pearson correlation of 1, regardless of the slope of the line. So if they fall exactly in a straight line, then that's a Pearson correlation of +1 if it's up and to the right. So that gives you kind of a sense of that. Now, the other thing that you see on this output is something called R square. And so basically that is essentially you take the R value, you take the Pearson correlation value of 0.536 and you square it. You could put that in your calculator. 0.536 times 0.536 is going to be equal to this R squared value of 0.287. That value is called the strength of association, is also known as the coefficient of determination. So just so you've heard those words, I will refer to it as R squared. But what it means is the proportion of variability in Y, or points on exam 2, that can be explained by X, or the points on exam 1. So knowing something about exam 1 tells us about 29% of the information that we need to know about points on exam 2. And so it's the proportion of variability in Y that is explained by X. That is a definition of R squared that's commonly used that you would be expected to know about. So that concludes our video on how to conduct Pearson correlation in SPSS.